Hi everyone. So the final two measures that we are going to calculate today are the standard deviation and the normal score. The standard deviation is a measure for which a single standard deviation exists for a given data set. The so-called normal score, standard score, or z-score, these are all names for the same thing, is something that we have on a per value basis. So basically every entry in our data set is going to have a unique standard score. And the reason for that is that the standard score basically is just explains how far from the mean a given value is in terms of standard deviation. So it uses the standard deviation as a unit to describe how far a given value is from the mean value. But in order to get that, we first have to create the standard. We first have to calculate the standard deviation. Now, we are going to do this from scratch, so be patient. But before we can calculate it, we first have to understand what it is. So this you'll see in your readings. This is part of the Wikipedia page of standard deviation, which I like because it gives us an opportunity to kind of just work backwards through a description of what the standard deviation is, which seems very complex at first, but if we just work through it step by step, it's actually fairly straightforward. So for this example, we're going to be using this definition. In fact, I might even go ahead and zoom in on it just so it's really big and easy to see. So the first thing that we want to look at is, and we do start at the end of the sentence here. So the first part of calculating standard deviation is to take the deviation of each value from the average value, okay? Deviation is just another word for difference, and of course in math, when we say difference, we mean subtraction. So the first thing that we're going to do in calculating the standard deviation is we are going to subtract each value we're going to subtract the average value, which of course is just another name for the mean, from each value in our data set. Okay, so how we're going to go about this practically, I'm going to go ahead and come here. I'm selecting in the letter part, right-clicking, and I'm going to say insert, and it's going to automatically insert a column. I'm going to label this one difference from mean. Okay, and I'm just going to do my calculation. So here I'm going to say equals, right? Because again, I'm doing a formula. I'm asking Excel to do a calculation, and it's going to be my particular value minus. Now here's where I want to make sure that I actually reference this cell minus the mean. Okay, so pretty simple, pretty handy. Now, fortunately, Excel is reasonably clever, and I can copy this formula down, and you'll notice that it has shifted, and now it's pointing to A3, right? So I don't have to manually type in this formula for every single cell. However, if you look closely, you'll notice that something else has happened. So in this cell, I was working with A2 and S2 because S2 is where my mean is. But when I moved the formula down one, it not only moved the A column reference down, so that's A3, it also is doing now minus S3. And that's a problem because S3 is not my median value, it's my mean value. So this is a great point to, this is a great moment to see how we can more closely control our formulas in Excel. So when we're using references, as they're written here, they will increment. If I were to paste it over a column, it would move all of the references over a column. So it tries to be a little intelligent about how it handles the formula as you give it. Now, in this case, we want part of the formula to change, but we want part of it to stay static. In other words, we want to make sure that we're always subtracting the value in S2, no matter what row we're on in our data. And the way that we do that is using a $sign. So the $sign, okay, before the column and the row is going to fix that part of the formula. So I don't actually need both $signs in this case because I'm only changing rows, and so it would be sufficient for me to put a $sign before the two. But I'm going to go ahead and do that just to be super careful. And so once I've added this $sign, what we'll see is that if I copy and paste this formula down, and I'm just doing like a control or Apple C, Apple V there, that although it has now switched to A3, it is still pointing to S2. It's still pointing to my mean, okay? This is a really handy thing in Excel. You're going to use it a lot. So now I copy it. Again, how you decide to copy it down is up to you. I prefer to select all the cells and hit paste. And we'll see that, unsurprisingly, obviously, as we get over the halfway mark. Because my mean and my median are close together in this data set, wouldn't necessarily be the halfway mark in other data sets, but I go from negative to positive values. So I've done the first bit of my calculations here. So I'm going to go back to my definition, and I'm going to work through the next part. So it says, okay, the deviations of the value from their average value, we just did that, the difference of each value from the mean. And now it says we have to square them. So that's pretty straightforward. In order to square them, I'm just going to create, once again, another column. And I'm going to call this square of difference. Okay. And how do I square something? Again, I'm just going to use the equal sign, and then I reference a cell. And of course, to square something, I just multiply it times itself. In this case, I don't need to worry about using that dollar sign because I'm only changing rows, right? I'm going to paste this down. I'm not referencing something in another column and row that I need to hold static, right? I'm always multiplying things against themselves. So I'm going to do that. Okay. Not so bad, hopefully, right? Just taking it step by step. And then I'm looking for the average of those squared deviations. Well, we certainly know how to do that. I can just do that by, let's see, I'm going to come over here. And I'm going to say average squared deviations, right? And it's going to equal what? Well, I'm just doing the average, so it's the mean, right? So the way that I do the mean in this case is I do the sum, right? So I'm going to do the sum of all my squares, right? I'm going to end my parentheses, and of course, I think that's all I'm doing. I'm just doing I'm doing the average. So I take the sum, I divide by 20 because I have 20 records. There is the average squared deviation. And if I flip back to my formula, it says the square root. I'm taking the square root of the average of the square deviation. Okay, so all I have to do is take the square root of this. And that square root is actually the standard deviation. And the formula in Excel is SQRT, I believe. Okay, and I'm just going to point it at the cell that has my squared. And there we go. The standard deviation of my data set is 547.5216, right? So what does this mean? In order to understand what this means, it's helpful to look back at our image here. I wish I could get rid of that bottom part. Can I expand this? No, I'm not going to. So the reason why this is valuable to us, why the standard deviation is meaningful, is because the standard deviation has a very special relationship to the mean and to the volume of data that we find within certain distances from the mean, within a certain number of standard deviations of the mean, when we're dealing with a standard distribution of data. That was a lot of words. The thing to look at here is to understand that 0 standard deviations from the mean is, of course, the mean, right? And what we're seeing here is that in a case where we have a standard distribution, we can expect, or we will find, that 68.27% of all of the data values fall within one standard deviation of the mean, okay? So that means if I take the value of the mean and then I add whatever the amount of one standard deviation is and I subtract whatever the amount of one standard deviation is, all of those data points, 68.27% of my data points will fall within those between those numbers. If I go out another couple of standard deviations, I get another 31.5% or so, right? So between 1 and 3 standard deviations of the mean, right? And we can go both negative and positive, of course, because it's symmetrical. Between 1 and 3 standard deviations, I'll get another 15.73%. And then past 3 standard deviations from the mean, we're talking about a very, very small fraction of the data is going to fall in that range. And what that means is that if we have a normally distributed data set or a standard distribution in our data, if we find something that falls more than 3 standard deviations from the mean or less than negative 3 standard deviations from the mean, there is something going on there, right? There is something very unusual about that situation. Again, sometimes if we find this, it's just an error, right? There's just something wrong with the data. But sometimes it means there's something more interesting going on. So this is the reason, because this distance from the mean has interpretive value, right? We want to calculate it. And so this process of saying how many standard deviations away from the mean is a particular value is the normal score or the standard score. And so we calculate this by just using the quantity of the standard deviation for a particular data set as the denominator. And we're saying how many standard deviations away from the mean is record X, right? So in this case, the way that I would do this is I would insert, once again, one more column. Oops, probably don't want to put it there. Kind of want to put it over here. Okay, and this is going to be the, I'm going to call it Z-score, standard score. All I have to do is say, look, how far is this value from the mean? I've already calculated that. And then how many standard deviations is that distance? And so I do that by dividing it by the standard deviation. And I get this value, 1.4, blah, 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 right? Now, in this case, again, we're going to want to use our cell freezing mechanism of the $sign because, again, I have a distinct value for each row. I'm going to have a distinct standard score for each row, but I have to always be dividing. The value by the standard deviation, so I need to lock that reference. Okay, and then once again, I can just copy and paste this all the way down. Okay. And what this reveals to me as I look at these values is nothing in here seems quite out of the ordinary if this is a normally distributed data set, right? I've got something that's very close. It's like 2.94, really, really almost 3 standard deviations from the mean. So probably, and I will note that this value as well, if I compare it to, say, my upper bound, the 2577, right, is actually a little outside of our upper bound as well. So there's a reason for us to think that perhaps there's something unusual about this trip. Obviously, we have no idea. We can't say at all right now what that might be, what might be unusual about it. But we can say that it is not typical of this data set, right? Now, huge caveats here. So many things about this data set are arbitrary. I just decided to take the first 10,000 rows and then look at the station 72 values within that, et cetera, et cetera, et cetera. But the process that we've gone through for this holds in any case, right? The mechanics of it will stay the same. It is up to you as the data journalist, as the person conducting the analysis, to make sure that when you select a data set, the frame of that data set has meaning, right? So we wouldn't just look at the first 10,000 rows, right? We might look at all of the rides on a particular day, or we might look at a particular set of days or types of days, right? We might look at weekends versus weekdays. That is all up to the care and judgment of you, the human, and has nothing to do with the math, right? So this is a process that we can apply to any set of data, but it is always on us to make sure that the frame that we have chosen for the data, essentially the data set that we have selected, has meaning. The last thing I just want to point out here is that there are ways to check all of these things, unsurprisingly. But again, it's up to us to do the sanity check, right, and make sure that things make sense. So for example, the Z-score is actually a great place to do this because if you look at this curve again, what you'll see again is that it's extremely unlikely to ever get something that is 4 standard deviations away from the mean. 3 is already pretty unlikely. If you find yourself with standard scores that are much greater than 4 or 5, or much less than -4 or -5, something is wrong, right? So we can never let ourselves be complacent about applying this math and say, well, that's what the math says, right? Because again, it's up to us to frame the data set in a meaningful way. It is up to us to check and make sure that the results of our formulas are actually sensible. This is really the primary way that you're ever going to catch errors. So with that, I look forward to seeing you all next week and going over some of this material in class.